Somewhere in the Pacific Ocean, a Japanese construction company is quietly preparing to build the longest object human beings have ever made, a structure that will stretch 96,000 kilometers into the sky, farther than the distance to the moon and back. And if they succeed, every rocket launch you have ever watched on television becomes obsolete overnight. Right now, as you read this, a fiber thinner than a strand of your hair is orbiting the Earth aboard the International Space Station, being tested against radiation, vacuum, and extreme heat, because that single thread of material is the only thing standing between this plan and complete failure. And the company betting everything on it has already built some of the tallest towers in Tokyo, which means when they say they can do this, the world has learned not to laugh. For 70 years, humanity has escaped gravity the same violent way, strapping people and cargo to a controlled explosion and hoping the math holds, burning through fuel worth millions of dollars in minutes, watching 90% of every rocket get discarded into the ocean or burned up in the atmosphere after a single use, because that is simply what it costs to leave this planet. $5 million in propellant just to reach orbit over 2007. $100 for every single kilogram sent into space, and that number has quietly strangled almost every ambitious idea humans have ever had about living beyond Earth, because you cannot build a colony, a factory, or a city among the stars when the shipping cost alone could bankrupt a nation. But what if the answer was never a bigger rocket? What if the answer was a cable? One continuous structure running from the surface of the ocean all the way out past geostationary orbit, held taut not by rockets, but by the simple, elegant physics of a spinning planet, a structure so long that objects could simply climb it, using electricity instead of exploding their way through the atmosphere. No fuel, no fire, no destruction, just a motor gripping a ribbon and quietly rising, and the projected cost per kilogram would collapse from $2,700 to somewhere around $10. This is not a concept sitting in a science fiction novel. This is an actual engineering roadmap from Obayashi Corporation, the same construction giant behind the Tokyo Skytree, one of the tallest structures ever built by human hands, and their target completion date is 2050. Which sounds impossibly close for something this audacious, until you understand exactly how they intend to build it, step by step. Starting not in space, but in a shipyard. Picture the scene. Workers in a coastal Japanese shipyard feeding 40mm thick steel plates into plasma cutters, each plate curved to the precise radius required to form a massive floating ring 400 meters across, larger than most stadiums, and this ring will become the Earthport, the ocean-based foundation from which the entire cable will eventually be anchored. 24 separate watertight compartments make up this ring, each one welded shut in complete isolation from the others. Because if even one of those chambers develops a leak once this structure is floating on open water, the consequences are not minor. An entire multi-billion-dollar port could tip, flood, and sink, so every single compartment is flood tested before it is ever allowed to leave the yard. No exceptions, no shortcuts. As the ring grows section by section, engineers demand that every joint align within 2 millimeters, an almost absurd level of precision for something this massive, and underwater welders complete the base joints, knowing those welds must survive decades of relentless equatorial ocean conditions without failure. Inside the hull, reinforcement frames are installed every 2 meters, because if this structure is allowed to flex even slightly under load, the cable mount at its center could fail catastrophically. And catastrophic failure here does not just mean losing a piece of hardware, it means losing the anchor point for the most expensive and ambitious structure ever built by human beings. To keep this 400-meter ring from capsizing in open water, workers pour 48,000 tons of concrete ballast into the base cells, essentially turning the bottom of the ring into dead weight that fights against the ocean's attempts to tip it over, and from inside those sealed compartments, workers have described the feeling as something closer to being inside a submarine than standing on a ship, because that is functionally what this structure is designed to be, a vessel engineered to endure the harshest ocean conditions on Earth for an entire century without failure. 12 separate thruster pods are mounted to the hull, giving operators the ability to actually steer this 400-meter ring through open ocean, keeping it stationed precisely on the equator where the physics of a space elevator actually work, because position here is not a preference. It is a requirement. Move even slightly off the equatorial line, and the entire tension system governing the cable above begins to destabilize. Once the deck sections are lowered into place, aligned, bolted, and welded, flush against the hull, workers begin threading ballast lines, fitting valves and flanges by hand, one connection at a time, because a structure meant to support the tallest object ever built by humans cannot afford a single overlooked detail. And that detail becomes brutally literal when you consider lightning. This cable, once complete, will be the tallest object on the entire planet, taller than any mountain, any tower, any structure ever conceived, and lightning does not ignore tall objects, it seeks them out, which is why lightning conductors are installed around the entire deck before anything else goes online. The mooring system alone, the chains that will eventually anchor this floating port against the pull of a 96,000 kilometer cable, weighs 6,000 tons, forged link by link from high-strength alloy steel. Because the tension these chains will one day be asked to withstand is almost impossible to comprehend using ordinary human intuition. When this hull finally leaves the shipyard for the first time, moving out into open water. Under its own power, workers line the deck and watch the coastline disappear, aware that they are witnessing the first physical piece of something that could redefine how humanity leaves this planet forever. At the center of the ring rises a 60-meter terminal tower, a lattice of steel reaching straight up from the platform, and inside its legs, workers' roots. Power cables and communication lines with obsessive precision because every circuit must be fully verified before the next system can even begin installation. And sensors are fitted along every single leg of that tower so that if the eventual cable so much as vibrates unexpectedly once it is attached, engineers 360 degrees away in a control room will know within seconds. Nearby, a climber loading dock takes shape, complete with guide rails and heavy locking arms, engineered to receive vehicles weighing up to 100 tons, docking directly from orbit, and everything built on this platform exists to serve one singular purpose: to grip an incoming cable descending from geostationary orbit and never, under any circumstances, let it go. This is not simply a construction site, it is the seed of an entire floating city, complete with a desalination plant, independent power generation, and a full sewage treatment system, all being built. Simultaneously, because 6 separate generator sets are installed below deck with one unbending requirement, this port can never lose power. Not for a moment, not ever, because if it does, everything connected to this cable above it becomes instantly vulnerable. A laser transmitter dish is assembled on deck, the very system that will one day beam a power upward to climbing. Vehicles ascending the finished cable and the cable entry seal, the opening around the tower slot where the actual ribbon will eventually pass through, is fitted with the understanding that violent equatorial storms will try relentlessly to force their way inside, and they will not succeed. A helideck is completed on the aft section of the platform, the only way personnel can reach or leave this remote structure during an emergency or a routine crew rotation. And inside the control room, every screen and every panel is fixed permanently into place, because from this room, port operations will run continuously for decades. When the completed Earth port finally reaches its final equatorial station, thrusters fire in careful sequence, mooring chains draw taut, and workers stand watching. The tension gauges climb, waiting, holding their breath, because this is the moment the floating foundation of the space elevator officially takes its position on Earth. But the true miracle of this entire project is not the port. It is the cable itself, and it does not begin in the ocean. It begins inside a laboratory, where chemical vapor deposition reactors grow carbon nanotube fiber 1, atom at a time, an almost meditative process that cannot be rushed, cannot be forced, and cannot tolerate a single structural defect, because a defect anywhere along this fiber becomes a fatal weak point, stretched across 96,000 kilometers of tension. That fiber is drawn continuously onto collection drums, then twisted into yarn, hundreds of individual strands combined, not simply bundled together, but deliberately twisted so that the load is shared evenly across every fiber. Because bundled strands fail independently, twisted strands fail together, or not at all, and that distinction is the difference between a structure that survives and one that catastrophically snaps. These yarns are then bound into ribbon form, heated rollers pressing a polymer matrix through the material to give it its final structural shape. And once that shape is set, a protective coating is deposited across every exposed surface, because without it, the relentless radiation of space strips away carbon bonds within months, silently destroying the one material this entire plan depends on. Every single section of this ribbon is imaged under an electron microscope before it is approved, because a microscopic gap in that coating is not a cosmetic flaw. It is a gap in survival itself. And after all of that, after reactors, twisting, coating, and inspection, the very first cable sent to orbit will weigh only 20 tons, less than a single loaded truck. And yet that 20-ton seed cable will eventually be asked to support more structural load than a skyscraper. An almost unbelievable ratio of weight to strength that only became physically possible because of carbon nanotube technology. That ribbon is wound onto precision spools under carefully controlled tension, because a single kink introduced during winding becomes a guaranteed failure point the moment deployment begins, and each spool is then sealed inside inert gas transport canisters, because oxygen itself is an enemy here, slowly degrading the ribbon on contact, so it travels enclosed in nitrogen from the moment it leaves the lab until the moment it reaches orbit. At the launch facility, every canister is inspected on arrival before being moved into a clean room, and from there into the spacecraft itself. where the deployment mechanism is cycled by hand again and again, because every single release point must be tested before this payload is ever allowed to go vertical. A motor and brake system controlling deployment speed is installed, dictating precisely how fast this priceless ribbon will fall toward the waiting port below once it reaches orbit. And finally, the fairing closes over 20 tons of carbon. Nanotube ribbon, sealing it away for a rocket ride that will carry the literal seed of a space elevator into the sky. Final checks run line by line. Every sensor, every drive mechanism verified by a team that understands there will be no second chance if something is missed. 300 tons of liquid oxygen load into the rocket's tanks. Service arms retract, the pad clears, and then ignition and this cable that took years to grow, atom by atom, rises into the sky, riding a column of fire, climbing first toward geostationary orbit, 36,000 kilometers above the surface of the Earth, before separation occurs and thrusters gently orient the spacecraft into position above nothing but open ocean far below. And this is where the real tension of this entire mission begins, because the spool starts turning, and ribbon begins feeding out in two directions simultaneously, downward toward Earth and upward toward a future counterweight, unspooling across 36,000 kilometers of open space, a ribbon thinner than a single strand of human hair, falling silently through a void where a single miscalculation could send it drifting uncontrollably off course forever. On the ocean below, the capture crew at the Earth port has been watching, waiting, tracking this descent on radar for days, until finally the ribbon enters detectable range beneath the cloud layer, and an aircraft moves in to snag it above the clouds before workers carefully lower it down to the deck. And in that single moment, this impossibly thin strand of material touches the surface of the Earth for the very first time, connecting an ocean platform in the Pacific to a fixed point in geostationary orbit, one unbroken structure spanning a distance that dwarfs anything humanity has ever physically built before. Workers thread that ribbon by hand into tensioning drums carefully, deliberately, one guide roller at a time, and once tension is fully applied, the ribbon pulls, taut, stretching in an unbroken line from the surface of the Pacific Ocean to geostationary orbit. And in that moment, it becomes, without exaggeration, the longest continuous structure human beings have ever created, achieved not through decades of construction, but through a single rocket launch. But a seed cable strong enough to hold a person is still far too fragile to hold a civilization, which means the real work has only just begun, because now this fragile ribbon has to grow layer by layer, climber by climber, into something capable of carrying real weight to orbit. The climbers themselves are built back in Japan, heavy steel chassis welded inside. Assembly jigs, fitted with magnetic linear motor units bolted directly onto the arms of the machine, the exact components that will grip the ribbon and physically drive each climb upward. Gripper rollers are mounted to the motor housings and checked by hand, every roller on both sides tested individually, because a single malfunctioning roller 30,000 kilometers above the ocean is not a problem you can simply pull over and fix. Laser receiver panels are mounted to the underside of every climber because these machines carry no fuel and no batteries, drawing all of their power instead from a laser beam transmitted up from the Earth port below, an entirely new way of moving mass through space that eliminates the need for combustion at any point in the journey. Thermal blankets wrap every exposed surface of the climber because the temperature swing these machines will endure, from sea level heat to the brutal cold of high orbit, spans nearly 400 degrees, and no unprotected component could survive that swing intact. A repair dispenser is fitted to the sidearm of every climbing unit because every single climber sent up this cable also carries additional ribbon material, bonding new reinforcement directly onto the structure as it ascends, meaning every climb up the cable is simultaneously a climb and a repair mission. Cargo lock jaws are installed and cycled repeatedly on the dock, engineered to secure up to 100 tons of payload for as long as 7 full days, and emergency brakes are fitted to every gripper arm. Because if power ever fails mid-climb, those brakes clamp instantly and the climber stops exactly where it is. Suspended, secured, and very deliberately, it does not fall. After a full electrical bench test, every drive energized, every sensor verified, every possible fault cleared, the very first climber is loaded for sea transport, chained down, bolted in place, and shipped across 3 weeks of ocean toward the equatorial port that has been waiting patiently for this exact moment. When it finally arrives, a crane swings the climber across from the supply vessel, guide rails catch it, and it settles into position, home at last. Workers thread the ribbon directly. Through the climber's slot, the grippers close, laser power locks onto the receiver panels, motors spin to life, and the climber grips the fragile ribbon and begins, slowly at first, then with steady mechanical confidence, to rise, and the ribbon holds. From this point forward, the cable factories in Japan never stop running because 510 separate reinforcement climbers must be built, loaded, and sent skyward, each one carrying a full spool of ribbon material to be bonded directly onto the existing structure, layer by layer, while a control room tracks every single climber's altitude and bond quality in real time. And if a bonding pass comes back weak, the climber stops immediately and redoes the section rather than risk a structural flaw in a cable meant to last a century. Returned climbers are serviced on the dock, worn rollers swapped out, inspection sensors recalibrated, before being sent right back onto the ribbon to continue the endless work of reinforcement. When satellites cross the cable's projected path, port thrusters fire in coordinated bursts, physically swinging the entire ribbon out of the way, an almost unbelievable feat of engineering considering the scale involved, and ground crews use contact trolleys to manually inspect every bond point below the clouds after every major storm. Replacing lightning-damaged ground straps is routine maintenance rather than emergency crisis, because on a structure this size, some amount of damage is simply an expected cost of operation, not a catastrophe. By the time the 100th climber is loaded, the ribbon at the tower guide has already doubled in diameter from its original seed thickness, and damping masses are clamped along calculated intervals of the structure, specifically to prevent dangerous resonance from building up when multiple climbers are running simultaneously along its length. Around year 6, the factories retool entirely to produce wider ribbon, because the cable has grown strong enough to support the heavier reinforcement spools this new width requires. And by the time 300 climbers have made the journey, workers are swapping in wider bore guide rollers because, quite simply, the cable has outgrown its own original terminal hardware. By year 14, the factories are producing their final thickness ribbon, and the cable, now nearing structural completion, can accept a full 100-ton load. And 1 year later, in year 15, something happens that changes the entire nature of this project forever. The first real cargo makes the ascent, not reinforcement ribbon this time, but actual station components, because the cable itself has finally become strong enough to carry the weight of humanity's next home in space. While climbers continue reinforcing the cable structure day and night, an entirely separate construction effort begins unfolding at geostationary orbit, where a station is being assembled module by module, each component built here on Earth and launched skyward by rocket. And there is a striking irony in that fact that engineers openly acknowledge that rockets, the very technology this elevator was built to replace, are the ones responsible for lifting the first pieces of that replacement into position. Each module docks in orbit with a mechanical certainty, latches engaging under the careful watch of a control room team 36,000 kilometers below, confirming lock after lock as this orbital outpost slowly takes shape. A gravity ring, assembled on Earth in segments and launched piece by piece, will one day spin in orbit to simulate something close to Martian gravity for the crew stationed there, while solar array trusses, hinged and pre-assembled on the ground, unfold, automatically once released into the vacuum of space. At geostationary altitude, construction climbers hold their exact position along the cable, while robotic arms reach outward, bolting frame sections together piece by piece, and remarkably, workers themselves travel to this altitude not by rocket, but by climbing the cable directly, fitting internal life support systems by hand in microgravity across grueling 8-day shifts that would be unthinkable using any previous method of reaching orbit. Cable guide bearings are threaded through every level of the station under construction, engineered with obsessive precision to ensure the ribbon itself can pass completely through the structure without ever making contact, because contact here means friction, and friction here means a structural failure with no possible rescue. Solar arrays deploy panel by panel, hinges releasing and locking in careful sequence, until finally the station stands complete at geostationary orbit, docking ports open and arrays fully deployed, an entire functioning city built at 36,000 kilometers above the Earth's surface, and the very first crew to complete their rotation. There returns home the same way they arrived, riding the cable itself, an 8-day journey up, an 8-day journey down, the very first of what Engineers Project will eventually become thousands upon thousands of ordinary passenger trips. Meanwhile, back on Earth, an entirely separate structure is quietly taking shape. A 12,500-ton counterweight, assembled block by block on the ground before being loaded, piece by piece, onto cargo climbers and sent skyward, every single kilogram checked and logged at the dock before departure. Because this counterweight is not decoration. It is the physical anchor that keeps the entire 96,000-kilometer cable under the correct tension through simple orbital mechanics, extending the structure further and further outward as more mass accumulates above geostationary orbit, and as it grows, tension at the terminal rises accordingly, monitored kilopascal by a control room team that understands exactly what catastrophic failure would mean for everything built beneath it. And then, finally, after seed cables and reinforcement climbers and orbital stations and counterweights, comes the moment this entire multi-decade project was truly built toward the first passenger climber, fitted out with actual seats, functioning life support, systems, and viewports offering a view no human being has ever witnessed from this particular vantage point, assembled panel by workers who understand this specific vehicle will soon carry actual people. A full passenger loading rehearsal takes place at the port dock, practiced over and over until the process becomes as fast and as safe as boarding any ordinary ship. Life support. Consumables loaded and inventoried item by item before the hatch is ever allowed to close. Final checks run across gripper alignment, power systems, and communications. Nothing left to chance, nothing assumed, because this is no longer a test flight of an unmanned prototype. This is a human being about to ride an elevator into space. On day 1, the climber rises through the atmosphere. By day 3, it passes through the punishing radiation of the Van Allen belts. And by day 8, after an 8-day journey, unlike anything in the history of human transportation, it finally reaches geostationary orbit. Every single meter of that ascent, tracked continuously from the port control room below, altitude climbing steadily, power beam holding steady, cabin pressure remaining stable, every single reading logged as completely nominal. At the geostationary station, a crew waits at the docking hatch as the climber finally appears below them after its 8-day ascent, a docking arm reaching out, latches engaging, hatch seal confirmed, and then, for the very first time in human history, the hatch opens, and a passenger steps directly from a cable stretching all the way back to the surface of the Pacific Ocean into a fully operational station in orbit, having never once ridden inside a rocket. A second climber loads immediately, following the exact same checklist, the exact same sequence, because what was once an unprecedented experimental first flight has now, quietly and remarkably, become routine operational procedure. And the Earth port that took years to build, tested, welded, joint by joint, is no longer simply a construction site. It is officially a terminal, connected to a station at geostationary orbit, connected to a counterweight far above with climbers actively running along a ribbon that stretches 96,000 kilometers into the sky, a fully functioning, continuously operating system. Satellites now reach orbit with no rocket underneath them at all, no flame, no violent noise, no discarded hardware falling back toward the ocean, simply a machine riding silently up a cable. And the number that once defined the entire economics of spaceflight, $2,700 per kilogram, has been replaced by a new number, roughly $10 per kilogram, a shift so dramatic that it does not simply improve the space industry, it fundamentally rewrites what is economically possible, beyond Earth's atmosphere. And because one ribbon, however extraordinary, was never going to be enough to support humanity's ambitions in space, a second port is already under construction, with a second cable already being planned, because the engineers behind this project understand something crucial. This is not a single miraculous achievement. It is the first working example of an entirely new form of infrastructure. Every single piece of what has been described here, every bolt, every weld, every meter of carbon nanotube ribbon, was built and installed by ordinary welders, climber mechanics, ribbon technicians, and control room crews working one careful step at a time, proving that a structure once dismissed as impossible, science fiction can, in fact, be engineered into physical reality using tools and skills that already exist today. And somewhere in the not-so-distant future, if this timeline holds, a crew bound for Mars will walk onto that same Pacific dock, ride that same cable 8 days up to geostationary orbit, and board a spacecraft waiting there, beginning their journey to another planet without a single rocket ever igniting beneath their feet. Because what was once only sketched on paper in a Tokyo design office has, quietly and methodically, been brought to life. If this story of engineering at the edge of what's possible fascinated you, subscribe now, because there are far stranger, far more ambitious projects than this one still waiting to be told.